So the benefit of me recording the lectures is that, oh, let's say you're taking notes, you're taking notes real fast and you wanted to double check something. I'm going to post this video to my YouTube channel, okay? And I'll show you exactly how to get to that. But what I'm also going to be doing this semester is I'm going to be revising my notes after the lecture. I'm going to be making short lectures that are on YouTube that are just about specific topics. And when we do these specific topics, there'll be no interruptions. It'll be just me, the camera doing the thing. And so if you had questions or like you're not clear on something, you can actually go quickly to that video on the YouTube site and be able to review it again and say, oh, that's what he said. Oh, I wrote that down wrong. Or, oh, you know, he really flubbed that during the lecture, but it makes a lot of sense now. So things like that will happen. And so we want to make sure that we have a way to do that. Okay. So I'm trying to keep up with the messaging here. I'll talk some more about me and my research later. So I want to leave that message there. And Sheila will be talking to us a little bit later about SI as soon as I get to that component, okay? So if you could chime in and say hi, please.
Hi, everyone. I'm going to be your SI leader.
Okay, so there we go. All right, so it's about time to start. We've got 77 of us here, so I'm going to go ahead and start. Hello, my name is Dr. David Irvin. I have a PhD in organic chemistry. This is my chosen field, okay? I love organic chemistry. I've been working in it for 30 years, okay? I have worked 10 years for the government, doing government research for both the Department of Energy and the Department of Defense. I've worked 11 years in industry doing everything from nanocomposites, explosives, to building a machine that is now producing 1 million square feet a year of material, of a polymer material. And then I've also done academic research, everything from conducting polymers to my current one, which is a flame-resistant polymer. So I have a broad level of experience. In your book, as we go through both semesters of organic chemistry, I've probably run about 75% of those reactions. So I can give you a little bit of insight into, oh, that'll never work, but, you know, or this works very well. And so I'm going to give those little kind of comments as we go, hopefully enticing you to maybe look a little deeper, study a little more, and maybe give you some, you know, bits of memory that you can like, oh, latch onto, oh yeah, he made a joke about that because this. And so that's how I know that mechanism works. Okay. So I also wanted to start with my Canvas site. So I'm going to go ahead and bring my Canvas site up as a shared site. And this is the go-to, let's see, Canvas site, share. All right, so this is, you should just be seeing my Canvas site here. And this is just for our class. Notice that this is section 253, 8 a.m. TR, Tuesday, Thursday. So make sure that, you know, you should only be invited to this one, but this one is just for our class, okay? And so that when you click on this live button lecture, it'll actually take you to our Zoom lectures, okay? When you click on the lecture videos, what's that's gonna do is that's gonna take you to the YouTube channel just for this class, okay? The YouTube channel just for this class will have all of our live lectures that we have every day. And then after that, there'll be a different channel, and I'll show you where that is, where those are the pre-recorded canned lectures. So this is our live lectures with questions and hopefully good comments and mistakes and you know a few jokes. But that is where you'll go for this. If you miss a class, you know, participation is not mandatory, but highly encouraged, because I will be actually lecturing through Zoom, through Top Hat, and that gives me the opportunity to ask embedded questions. So I'll talk to you about that in a little bit. So again, the other thing about Canvas here is this is your book and homework, okay? So this button will take you to Top Hat. So you gotta go ahead and sign up for Top Hat, and it's an electronic book that is $70 that you should have a lifetime access to as a Top Hat user. And what you'll end up seeing is, this is my view with all the different things I have, but what you'll see is only things that are assigned, okay? And so if we look right here, we have an assignment, and this is the module 1 reading assignment. This is actually our homework too. So as you're reading, you can go ahead and answer the questions, okay? And so those responses are remembered and graded, and so that counts as our homework. So as you go through this, you read it, you maybe click on a video or two, watch the video unfold, and then when you get to the question, try to answer it with just what you've just read, okay? If you answered it correctly, that means you understood the previous section and you can move on. If you got it wrong, go back, read that section, figure out why it's wrong, and try again. You'll get 2 chances to get the grade right, and you'll have a prompt at whether or not you got it right. And so, for example, going along here, it'll give you this question here: which elements are correctly assigned on here? And so that you would go and say, oh, well, hydrogen is 1C, and then it'll tell you if that is right or wrong, okay? So if you use this as a tool of, did I understand the previous section, then you will have a higher chance of success at getting to the, getting a little deeper and understanding what you do understand and understanding what you don't understand, okay? And so those will just continue on and try to stay, about where we are in the lecture, maybe a little ahead. Me personally, I always like to read the book first and maybe not even answer the questions, go to the lecture, because I'm good at my first exposure here on the book. And I'm like, okay, I get some of that. I don't see how it all fits together. Go to the lecture. Hopefully that kind of knits a whole bunch of stuff together. And then when I go back and answer the questions, it's like, okay, yeah, okay, this piece goes here, this piece goes here, this piece goes here, and it kind of works together. And now you've seen it 3 times in 3 different ways, and you're more likely to remember it. Organic chemistry is not a memorization thing, it's a learning thing, and it's a process. So it's a little harder just to memorize. So make sure you find a way in which you study best that lets you see it 1, 2, or maybe even 3 times. Okay, so this is our homework. And so what I'm going to do is I'm going to go back. So the homework is embedded in the book. So that's great. There's no additional thing there. And that's all here. Throughout the semester, we're going to have 4 activities. What these are going to be Zoom breakout rooms where you collectively do activities together. And when those are assigned, you'll go to the activities button and they will appear here. And then after the assignment is due, they'll also have a key to see if you got it right. Okay. The point of the activities is, number 1, to be a little social. You're going to be in little groups of 5. You get to talk and say something. Number 2, you get a different student's perspective on things. Okay. And these are going to be during regular class time. So it's not a separate thing like SI. It's during regular class time. And then it's graded mostly for participation. So the idea is to just come, do the activity, get some answers on the page, and then look at the answers at the end to see if you got them right. Okay. So let's go back to a home page. So as we go to the thing here, this is the lecture and exams schedule. So this is where we should be. These are going to be plus or minus a day. I'll keep this updated as we go, but this is pretty much when we have it. It also has when our homeworks are due, when our activities are, and when our exams are. Okay. So I will not be sending out weekly emails. I used to do that, and it drove students crazy because they'd lose the email. So I put everything on buttons in Canvas. Everything is on Canvas. Go to our site. Boom, you'll know what's due next. In fact, if you look under the assignments tab, these are all the assignments we'll have, and these are when they're due, and they should pop up as they are like 1 week out or 2 week out, depending on how you've assigned it in your Canvas. Say, oh, look, I have homework coming up next week. I better start reading that, or make sure I get to do that. So this is how you can find all your assignments, when we're going to do things, when the exams are, which lectures are going to be which. Then, of course, we have the syllabus. I hope I got all of the mistakes out. I think it's right now, so we'll see. But it also has a section about Top Hat, and it has a section about SI. Okay. Now, Sheila will be talking a little bit about that, so I'll let her do that. Then additional resources button. There's some stuff like my organic nomenclature slide. So we're gonna hit that really hard in chapter 2. And so there's a place to review this. There's also hot topics for each exam. These are the big things that I think are really kind of, uh, the things that I really want you to focus on. And then there's this one right here, functional groups to know. That's going to be very important in chapter 2. So these are the things that you'll be, going to as you can. Hey, we're up to 83 people. That's great. Okay, and then the last thing that's going to happen here is this is still not fully active, but by next week, you should start seeing what I call full videos. And these are set aside. These are the exact same notes I'll be using in class, but it's a more scripted talk. Okay, so it'll be just what we were talking about on that day. And they're going to be shorter videos. I'm going to try to keep them all under 7 minutes. The reason is I'll focus on one single topic and I'll clearly define that topic in the title. So if that's what you're having trouble with, just go to the 5-minute video, 7-minute video, and look at just that topic. And so that will help reinforce what you may or may not be understanding in that particular topic. Okay. All right. Are there any questions about the Canvas site? Is the homework for later weeks open already? Not exactly at this time. They will be soon. I just have to, I wanted to change homework in chapters 5 and 6. And once I change the chapters in 5 and 6, I'll open those up for the rest of the semester. Yes. And I will open up all the books at that point, as soon as I double check all of my homework. But that's the one thing I want to do before that happens. That's a good question. On Top Hat, in the section, you should have 2 things for review, which are the slides I'll be using in class. These are the PowerPoint slides that I'll be using in class. Then the book will be assigned as a graded assignment until that assignment due date has passed. And then it'll be for review. You'll be able to come back to it forever. Okay. And so what you'll see is that these slides, which I'll start in today, will be found on the Canvas website, and I will be presenting through Canvas as well. Okay, does that answer that question? Do lecture recordings expire? I will keep the lecture recordings on the YouTube channel until a week past the final exam. Okay, so the reason I do that is that, there's going to be people's faces and stuff. And so eventually I want to pull it down, but I just wanted to have it for us for this class through the end of finals week. Okay. Let's see. I think that answered all the questions there. So I'm going to stop sharing this screen for now. Let's see. Come on. Stop sharing. And Shima, would you like to go now and talk about SI?
Yeah, sure.
Sorry, Sheila.
Yeah, no problem.
Do you want me to share screen or?
No, I'll just make it brief.
Okay.
I sent them an email yesterday. So hello, everyone. My name is Sheila Jimenez, and I'm going to be your SI leader for this course. So basically, you're going to see me here every Tuesday, Thursday, alongside you guys, bright and early, taking notes and reviewing the material myself. I sent out an email yesterday for the beginning of term survey that allows you to pick your SI session. And we want you to be consistent with your SI session. So you want to pick something that you can do every week. So specifically in this course with Professor Irvin, SI is going to be 9% of your grade. So you you have to attend 10 sessions to receive those that 9%. And it is voluntary. You don't have to come, but we prefer that you do because it is very beneficial to you all. And some students have earned up to half to a whole letter grade better than those that did not show up. As Professor Irvin had said earlier, the more times you go through OCHEM, the better it's going to be for you. So SI is just another way to help you improve your grade. Make sure that material is solid in your head. So in case you can't attend one of the sessions, you can always have a max of 2 hours per week. And that can count towards that 10 sessions that are required by April 11th. On the syllabus, it says April 9th, but we allow also the weekends because sometimes there's, well, I mean, if he puts in the, are you going to put it in at 9 on the 9th?
Yeah, it's going to be the correct number because they got shifted because
Okay.
of the Martin Luther King holiday.
Okay, great. So the 9th then. And then, so the survey is going to be open on Wednesday at 7 p.m. and it closes on Friday at 8 a.m. So you want to make sure that you fill that out as soon as possible, as soon as you know your availability, because it's kind of a first come, first serve basis. And they fill up really quickly. So you want to make sure you get that all done for you. And lastly, I am here for all of you. I received an A in this class. And if you guys have any questions or anything like that, feel free to message me, email me, and I'll be here for you guys as well. Okay. Professor Irvin.
All right. Thank you very much. Let me stress that SI is really a powerful tool because it's a peer-to-peer teaching. And she will have, lesson plans that kind of focus kind of on what we're doing or following what we're doing. And so this is really valuable tool because then you can actually, there's smaller groups. And so that, if you're shy about, having your camera on or asking questions, this gives you a great opportunity to ask questions, talk to your other students. I didn't understand this, and somebody looks at it a different way and boom, we can do it. And the lessons plans are designed to kind of support things that I think you're probably not, getting as well or needed a little more time. And so it's a really valuable tool to help you get a lot of extra, kind of time in there. I have not taken attendance for the class yet, but as soon as I start Top Hat, I can, those who already have it can take attendance. I don't take attendance the first week, but as soon as you get Top Hat, we actually have some cool features inside of Top Hat that will be being able to answer questions with your phone or your computer if you have it open. Okay. I think that was a question there. All right, so we've talked about Canvas site. We've talked about the fact that these will be recorded and posted to YouTube for later review. And we've talked about the SI session. So those things together, you have a single focus point to get all of your information, Canvas. You have supplementary information on the YouTube channels that I'll have there. And then you also have me as a resource. I will start, I don't have any setup office hours yet, but what I'd like to do is have you email me when you have questions. And then what I can do is I'll set up a survey next week and I'll try to figure out a time, obviously not 8 a.m., when we can have like a kind of a small group office hour where you can come and ask questions saying, okay, I was late to class, I saw the video, but I have a question about this. And so that way we can, make, things happen. Also, in this land of COVID here, if you get sick, this gives you a great opportunity to go back and catch up once you feel better. So I think that is another great opportunity we have with us with these recordings so that you can, keep on task if you can. If you can't keep on task, go ahead and back up and try to catch up as when you can. All right. Are there any questions about how the course is structured or where to get access to your information? Okay, I think everything in the chat is answered. I think that I have a question in the chat about PowerPoints, and I think what I'll do is I'll actually upload the PowerPoints as PDF for the first 2 chapters to the Canvas site, just to give everybody an opportunity to get to Top Hat loaded on. Top Hat's going to be very important because it also is where we do our exams. Okay, I've had a lot of people who have a lot of trouble with Examity, but I found the platform on that we use on Top Hat is a great testing platform, and there will be it has very few issues. The 3 issues I've ever had on the Top Hat testing platform was occasionally there's a login error, which usually can be fixed fairly quickly. Second one is every once in a while, one of the pictures drops out. And I think I fixed all those. And every once in a while, it'll kick you out because you went too far to one side of the screen or the other. And it'll kick you out, but then I can let you back in. So those are the only issues I've had. We haven't had people get yelled at and have their credit card number stolen like on that other site. So we're looking pretty good here. The lecture videos will be posted on YouTube, and that link is on the Canvas site. So you should be able to always access those. If you have access to the Canvas site, you should be able to directly go there. And if you go and subscribe to that channel, you'll just know when it is. Okay. Not that I'm fishing for, subscriptions. I don't need that, but I just, it lets you know when they're there. So I usually try to upload the videos the same day. Typically, I let it convert and then I upload it, probably start uploading around 30 minutes after class. That's the, okay. Okay, yeah, I will, again, I'll put those in there. If you didn't get an email about SI sessions, go ahead and email me and I'll forward that to Sheila and make sure that you get that, okay? All right. So any questions about the format right now? Okay. All right. So what I'd like to do is I'd like to shift my screens here and go ahead and try to present slides in Top Hat. So this is, as everybody gets Top Hat, I'm not going to take attendance or anything today, but as we get to this where everybody has it, you actually have this Top Hat join code. And when this Top Hat join code, you log in, you actually get to see this exact presentation and these slides. Oh, I need to share screen, don't I? Haha. Share screen. No, I want to do that one. There we go. Share. All right. So there we go. I'm sharing. This is just the Top Hat link that I had in my Canvas site, and then I clicked on the slides, and then I clicked on start presentation. I have a presentation mode, and so I am doing that right now. So what I'm going to do is I'm going to actually lecture from these Top Hat slides for the first couple slides, and then I'd like to ask, I'm going to send out an email about feedback saying, do you like this? Do you think it's working, etc. Okay. All right, great. Okay, so let's talk about organic chemistry. So if you want to go ahead and join code here, and then I can go ahead and take attendance. For the take attendance, I think it has something where you can do any of these things and it'll take attendance. And so if you already have Top Hat, go ahead and jam that in, do that. And so we can see if, oh, we got 50 people have signed up for Top Hat so far, and we have a lot of people doing it. So that's great. I'm going to minimize it, keep this open so that you can see that. And then I'm going to start the presentation. Okay. All right. There we go. Let's go back one slide. Come on. Okay. So today we're going to be talking about organic chemistry 1. And so what we're going to start with is number 1, what is organic chemistry? And what bonds are, the nature of bonds. The nature of bonds and the nature of where they form and how they form is the basis of most of the reactions we're going to do here. Okay, and so knowing that bonds are made up of electrons and knowing where electrons exist in an atom is crucial to knowing, number 1, the reactivity of a compound, the size of a compound, whether or not the bond is polar. And we'll talk about all these soon. What the shape of the compound is and which bond is most likely to react. So all these things have everything to do with where the electrons are. And so knowing this is why our base structure is this. We start here because this is what's going to tell us the most about where to begin with these materials. All right, next. Okay, there we go. There we go. So this is module 1. And of course, there's a lot of other stuff in the text. This is just the view that I'm going to give. I'm going to hit the highlights and some of the visual things. So there's additional verbiage in the book that helps you give a, get some, maybe a little bit of insight or kind of thread some things together. So always, take what I say and then read the book and then look at it again. And it should start to make sense. If it's not, go ahead and email me and we'll set up some office hours. All right. So atomic orbitals. So you've already taken chemistry, you know that atoms have orbital and they have different orbital levels, okay? Now, because of the Heisenberg uncertainty principle, you either know where the electron is or the energy of the electron, but not both at the same time. So when we're talking about atomic orbitals, it's where the electron is that's most important. All right, okay. So knowing where these electrons are, knowing where they might exist. So orbitals really aren't these hard shells of anything. What they are is the probability that the electron will be somewhere in that space, okay? And so it's not like, there's this hard shell, but the electron's moving around so fast that at any point in time, it could be anywhere on that surface, and therefore that surface is where you'll see that electron repulsion, which gives us our matter. Okay, there we go. So when you take some really cool math and you figure out what the shape of the different orbitals are, we ended up with getting different shapes, sizes, and they occupy different parts in space. So the simplest orbital we have is what we call the s orbital, and it's a spherical orbital, okay? And in this spherical orbital, we can have up to 2 electrons, okay? Because there's only a space for these 2 electrons, and these 2 electrons have to be configured in a specific way. And we'll talk about that as well. Now, once you go to the next level orbital up, this is called a p orbital, and sometimes it looks like a dumbbell, but because it's kind of got a linear axis to it, we can align these by 3 different locations on the x-axis, the y-axis, and the z-axis. Therefore, we have 3 different orbitals in the p, each of which will have 2 electrons in it. So that means we have a total of 6 electrons in the p orbital. So 2 electrons in the s orbital, 6 electrons in the p orbital. Now, we don't use these very much in organic chemistry, but when we talk about sulfur and phosphorus, we actually have access to what we call the d orbitals. Now, these have many more shapes, and there can be 10 electrons in that whole system. So that's why sometimes when we work with sulfur and phosphorus, we'll have more than 4 bonds to something. But it's all because those d orbitals are having a different shape. Okay. So every electronic orbital has what we call quantum numbers, okay? So the first quantum number is what we call the principal quantum number, and it tells you what the energy of the orbital is. So we start at 1, because that's our lowest energy orbital, and then as we move out from the nucleus, we go energy orbital 1, energy orbital 2, energy orbital 3, energy orbital 4, okay? The second quantum number we have is what we call the angular momentum one, and this tells us what the shape is, okay? So the number for the angular momentum is the energy minus 1. So that it's always going to be n minus 1. That means the lowest shaped orbital is going to be called 0, okay? And that equates to the s orbital, the spherical orbital, okay? Now, when we go up to the 1, that equates to the p orbital, 2 is the d orbital, 3 is the f orbital. Again, the most important ones for us are going to be the s, the p, and the d. So we need to make sure we have those. The next thing we have is what we call the magnetic quantum number. The magnetic quantum number is the orbital direction, okay? So the orbital direction can be a set of numbers based on the orbital shape. So if we have s, that means we only have a magnetic number of 0 because we only have that. And that means we can only have 2 electrons in that system. If we go to 1, our magnetic orbital or direction numbers can be -1, 0, and 1. That means we have 3 different orbitals that we can put 2 electrons in each. And so that's how we can see how we can build the number of electrons in each of these shells. Okay. Now, the last thing we have, which is written up here, is we have spin. And spin just means that whenever you have an electron moving around, it's creating an electric field and a magnetic field, okay? And so it makes its own electric field and has a north and south pole. So if a spin of 1/2, just imagine it's always the north pole is facing up. A spin of -1/2 is the north pole facing down. This allows us to pair up electrons without using up too much energy. Okay. Okay. Let's see. Hang on. I want to minimize this. All right. And I want the chat. Okay. There we go. So let's go back to present. Okay, hopefully there we go. I actually had covered up my chat. I wanted to make sure that people could see. There we go. All right, so we just finished this description here. Now let me show you what that looks like. I'm a very visual person, so I always like to have a little kind of diagram to tell me what we have. So remember, we had those 4 numbers that we had with our quantum numbers. And so we had energy level, shape, then we had the magnetic, which tells us how many pairs of electrons we can have. And then we had whether or not they had spin on them or not. So if we look at this visually, we can see that the lowest energy orbital is always going to be our 1s. So it's our 1 orbital. And because we only have 1, the only shape we're allowed to have is the s orbital or the sphere. Okay. When we move up to the next one, that allows us to have up to 2 different kinds of orbitals. We have the spherical orbital plus the dumbbell orbital. But remember that dumbbell orbital had a value of 1. So that means we can have 1, 0, or -1. So we have 3 different orbitals here. And if we go up again, D had a value of 2, which means we have -2, -1, 0, 1, and 2, giving us a total of 5 orbitals available to us. Okay, so that's how those quantum numbers look in a visual representation. Okay, now if we think about just a single electron right here, notice how these energy levels appear to be the same. Okay, because there's no electrons in there, they actually are kind of mythical and they just kind of exist, but they don't actually have a true energy associated with it. However, once you start populating those and adding electrons to the system, what you'll see is these energy levels start spreading out. And so if we look here, our s orbital is actually a little bit lower in energy, but now our 2s is lower energy than our 2p. Okay, this becomes important as we start building things with electrons in these orbitals. And then as we go up, notice how these are spreading out even more and more as we're adding these new types of orbitals. We're adding and their energy is spreading out even more. So what we'll see here is this spreading out of energy is controlled by the idea that Mother Nature is lazy. Mother Nature wants to conserve as much energy as possible. And so we always fill from the bottom up. And as we do that, we're going to see these differences in energies because they are slightly different places in space. Okay. So let's go ahead and try this. I'm going to start this question. Go ahead and see if you can type in with that code you have, either text with this response or use the code that's already in there, and see if you can answer the question. CC is the question, and the answer is A, of course. So let's see how many. Oh, okay, so a lot of people can do this. So what I'll be doing is I'll be embedding these questions to see if you're getting a certain topic, okay? And okay, almost everybody's assigned. So I'm gonna go ahead and give it a couple more seconds. And then I can view responses. And everybody who responded to respond to the correct one. So great, all right. So next lecture, I'll actually have a question about this particular topic. And so if a lot of people are getting it right, then great, I can move on. If not, I'll go ahead and explain it a little bit more. Okay. All right, so let's move on to the next slide. There we go. All right, so now that we have this visualization about how the orbitals are arranged, with the lowest energy orbital 1s being at the lowest energy and then kind of moving up as we go, let's talk about some rules of filling these orbitals. These rules of filling orbitals are going to help us decide how many electrons we have available to bond. So that's why we want to do this. The first thing we want to do is that you are, again, nature is lazy, you populate the lowest orbitals first, okay? So in this case here, we would have 2 electrons in our system. We have our 1s orbital, which is of the 2 electrons available. And instead of having 1 in the 2s and 1 in the 1s, let's see if I can, instead of having like here, okay, where is it? One here and one here, that doesn't happen because that electron is in a higher energy orbital. It took more energy to put it there, so it's not going to happen. It's going to be in the lowest energy orbital. But look how we've done this, okay? We have it so that our spins are opposite each other, okay? So if we can imagine that we have 2 electrons and they both have a negative charge, what do they want to do? They want to repel each other, right? Okay, so just trying to stick 2 electrons together would be very difficult because they have electron-electron repulsion, that negative charge repulsion. However, we overcome some of that by having those 2 magnetic poles, and so now the North Pole and the South Pole are aligned. That takes away some of the energy difference and allows us to what we call spin pair electrons. Okay, so that's where that half, plus 1/2 and minus 1/2 comes in. So we're not going to do it where we have 2 electrons split. We're going to try to spin couple the electrons at the lowest energy level first. All right. So the next thing we want to do is we want to try to populate orbitals to maximize the total electron spin. What this means is it takes energy to spin pair. Okay, so if we're taking energy to spin pair, wouldn't it be easier to put electrons in all of the orbitals of an equal energy? Notice that we have 3 of these 2p orbitals. All 3 of these 2p orbitals have exactly the same energy. So we're not losing any energy by putting 1 electron in each. We're being able to put 1 electron in each and not lose any energy. Here, we had to use some energy to spin couple, okay? So that's why this is not how we fill an orbital. And then we also notice that our spins are not aligned here, okay? We don't do that either. So notice all 3 spins are up and we have all 3 in individual orbitals before they start spinning. Now, if we add another electron, we're going to add it, we're going to spin couple it to one of those, but it has to be oppositely in the opposite spin. Okay, so the next rule is spins, okay? We must have the 2 electrons, if they're occupying the same orbital, because if they're spinning in the same direction, they're going to want to repel each other. Because of the magnetic component, they can be slightly less energy to spin couple. So they must always be a plus 1/2 and a minus 1/2. You're never going to have the 2 pluses or 2 minuses in an orbital. Okay. So what does that tell us now? Now we have the basic set of rules for how to put any number of electrons in any atom we have. Okay, so instead of memorizing this, let's use the periodic table to build it for us so that we know exactly where things are, okay? So what I like to do is look at the periodic table here, and this is our first 2 columns here. Our first 2 columns here are are called 1 and 2, or 1a and 2a, and that's where the s orbitals are, okay? And starting from the top down, this is our lowest energy orbital, and then these are increasing in energy, okay? So in our first set here, we have hydrogen, which only has 1 electron in its 1s orbital in its elemental state. Okay. Now, turns out helium which is the next one over here, has 2 electrons in it and it is way over here. But we've put it over here on the periodic table because it has a filled orbital. And so as we'll go through this, all of these on this side are going to have filled orbitals. And I'll talk a little bit more about that, but that's why, but really you can actually put it here because that makes it 2 electrons in this S if you wanted to. In fact, some periodic tables have them in both places. Okay. So the next most important thing we need to look at is this next level here. This is the 2 level. This is where a lot of our electrons are going to be. We have 2 electrons, so we have to fill the S first, and then we can start filling this P. We have a total of 6 electrons we can put in this 2p orbital. Once we fill that orbital, we now have our noble gas right here of neon. No, argon. No, neon. I forgot. I'll see. So we have to put an electron in here first, then put our second electron here, third electron here, fourth electron here, fifth, sixth, seventh, eighth, ninth, 10th. And so that's how we can build our electronic structure for any compound just using the periodic table. Okay, so let's talk about what that would look like, okay? So it wasn't yet, yay. Okay, so the way we would do that is we have our energy level first, the shape of the orbital, and then how many electrons are there. So if we look at this, we have our first energy level, the shape of that energy level, and how many electrons we can have, okay? And so we have 2. So that's a completely filled orbital. So if we look back here, that means we've already added 2 electrons to the system and we filled this orbital. And now we have to go to the second level of energy. So we're going to start with our 2s. So now we start with our 2 energy level, our s shape, and then we only have 2 electrons we can put in an s orbital. So that orbital is now filled. So now we need to start filling the p's. So we have our 2 energy level, our p, and then we can put up to 6 electrons in that system. And let's say, oh, well, we have another electron to balance out our core. And so we have to go down to our next energy level. So we have to go to our 3 and start putting our first electron in this 3s orbital. And so that would mean that for this one right here, we are giving our, we are following all our rules for assigning these electrons exactly where they are. And excuse me, hang on. Okay, chemists are, harried, lazy, whatever you want to call it. We can actually take the complete filled orbital of the previous noble gas and say, okay, we know that it's filled up completely to that noble gas and only add the electrons above and beyond that. So that's what we get to this condensed electronic configuration word. So this is what we would call our electronic configuration. And this is our condensed electronic configuration. Okay, so now we want to introduce another concept, okay? And that's the difference between valence electrons and core electrons, okay? Core electrons are the electrons that are in filled orbitals. So if we had 2 electrons in a 1s orbital and that was filled, we have helium. That's a noble gas. Those are considered core electrons. They're core electrons because they have a completely filled orbital and they do not participate in bonding, okay? All the electrons that are in non-filled orbitals are available for bonding because those are what we call our valence electrons, okay? Those are on the outside of the edge and they want to fill that orbital somehow. And most of the time they fill it by either bonding or gaining or losing an electron to form an ion. Okay, so knowing how to build this and getting to how many electrons are in that valence electron shell is going to tell us a lot about the size, shape, and how many times it'll bond in the system. Okay, so again, the valence shell is that outermost level of electrons that are not full. Okay, so you have to have an electron in it and it can't be full. If it was full, it's what we call a core shell. And those don't involve in bonding. Valence electrons are all the electrons in that outer shell. So for example, carbon is what we call a group 4a, And therefore, that means it has 4 valence electrons available for bonding, okay? That number 4 is very important for us because that tells us how many times it will bond and how many bonds it will make. Nitrogen is the A5 right here. And therefore, we have 5 valence electrons, and all the halogens have 7 electrons here, okay? All right, so that group number, the A group number, tells us what we have. So you don't have to memorize this thing. You just need a periodic table. So your hydrogen has a 1 electron in an s orbital. Your oxygen has 6 electrons in its valence orbital. Phosphorus, right here, has 5 electrons in its valence orbital. Okay, so all you have to do is know what the A number is. Boron has 3 electrons in its valence orbital. Don't have to memorize anything. Look at the periodic table. That column will tell you. Now remember, this has either 2 or 8 electrons in here. Those are filled orbitals. These are core electrons because these are completely full. So those are core electrons. Everything else that doesn't have that filled shell is our valence electron. Okay, so the valence electrons are the ones that do all the bonding. So knowing where they are, go back and study. Make sure you can correctly identify how many valence electrons we have, because that is going to tell you something about the bonding, the shape, and availability. All right, questions on that? Any comments on the chat or anything? Okay. All right, so now that we know that the electrons do the bonding, and now that we know only the valence electrons do the bonding, let's talk about the different types of bonding we have in organic chemistry. Technically, we have a continuum or a spectrum of bonds, okay? Everything from what we call covalent, non-polar covalent bonds all the way to an ionic bond, okay? And we have definitions that tells us what these are. Most of the time in organic chemistry, we do have ionic bonding, covalent bonding, and what we'll see is there's different types of covalent bonding, specifically non-polar and polar. And that tells us everything about the reactivity of the molecule. Okay, so in ionic bonding, it's kind of what we did in general chemistry, is the idea that you either gained or lost an electron to form an ion. Okay, why do we do this? Well, if we look at our sodium atom here, we have the, the 2 orbitals completely full, just like we saw in that example before where we saw that we only had 1 electron in our 3s orbital. And so the core electrons were completely there, and we have 1 valence electron. Okay, so it can do 2 things. It can add an electron to here to fill this orbital. It can share an electron to fill this orbital, or in the case of sodium, it actually loses an electron to have an empty orbital. So now its 2 orbital is completely full. So now it's happy, it has a full orbital, but it also has a positive charge. Okay. Okay, so in the case of chlorine here, we don't have a filled orbital. We have 1 electron missing from this P, and so it kind of wants the electron. So it's willing to accept the electron, have a full orbital, full 8 electrons in its outer shell, and accept a negative charge. Now, the cool thing here is that your negative charge and your positive charge are attracted to each other, and so they counterbalance each other out. And so ionic bonding is all about losing or gaining electrons, not sharing electrons. Okay. So how do we know what it's going to do? Well, it turns out each atom has a certain electronegativity, or a certain amount of how much it really, really wants electrons, okay? And the scale goes from about 4 for fluorine all the way down to less than 1 for some of the metals right here. And this difference in electronegativity is important to tell us what type of bond we're going to form. Are we going to have a non-polar bond? Are we going to have a polar bond? Are we going to have an ionic bond? That is all controlled by the electronegativity. The cool thing is that you can usually see it by looking at the difference in the, by calculating it out. So if you have 2 atoms, atom X, or okay, that's atom Y, and you have atom X right here, okay, and you take the electronegativity of atom X and you take the electronegativity of atom Y, and that difference in electronegativity is less than 0.5, we have by definition a non-polar covalent bond. Okay, meaning that they both want the electrons about the same amount, so neither one is pulling more or less electron density toward it, therefore giving us a non-polar covalent bond. Now, think about this. Non-polar covalent bonds are less reactive than polar covalent bonds. We're going to see this time and time again. Okay. So what if we took the difference between atom X and atom Y here, and it was between 0.5 and 2, okay? Or 1.9 or 2 right here. This means we still are sharing electrons. When we share electrons, we have a covalent bond, but we now have a polar bond. One of the two atoms wants the electrons more, has poured more electron density toward it, and therefore is more likely to, it has a bond where part of the bond is partially positive, part of the bond is partially negative, because the one that wants the electrons more is pulling more electrons. Now, once you go for a difference above 2, it's just easier to give the electron away and form ions. And so we typically call those ionic bonds. Okay, so that's the definition between them. And we're going to see this time and time again as we move through. Okay, so I said that when we have a polar bond, that makes one of the atoms have more of the electrons on it. So when we visualize that, we can look at something like this. In this case here, okay, now I'm doing straight lines. That's weird. All right, in this case here, let me do that. We have two atoms. They both have an electronegativity of 4, okay? They're both really want the electrons, okay? But if we look at the difference between those two atoms, they're exactly the same. They have a 0 difference, and therefore they make a non-polar bond. They both have the same amount of electron density on them. However, if we move to something like HF, hydrogen has an electronegativity of just over 2. Fluorine has an electronegativity of about 4. So that's almost as polar a bond as you can get and still be covalent, okay? But look what it does to the sides of the molecule. Because so much of the electrons are being pulled toward the fluorine because it wants electrons more, this side is electropositive and this side is electronegative. So we typically denote that by, blue on the positive side and red on the negative side. But notice it's not just a blue dot and a red dot. There's actually a gradient there. So at the far end of the hydrogen is the most positive side of the molecule, and the far end of the fluorine is the most negative side of the molecule. Okay. Now, if we put this molecule here into an ionizing solution, like let's say add it to water, we can actually force it over the hump and turn it into true ionic, a true ionic system. In this case here, we're adding lithium, which is just a little less electronegative than hydrogen. That kicks it over the 2 mark, and therefore this is a true ionic compound. And those are denoted by a full positive charge and a full negative charge on the atom. Okay, so does everybody understand the difference between bond polarity, ionic bonding, and the covalent bonding that can be polar? There's a thumbs up emoji there somewhere. Okay. All right. So let's talk about covalent bonding, okay? Because that's the one we find most often in organic chemistry. Although we do have ions, this is the one we want to deal with the most, okay? So the idea here is that if you have a shell that is not quite full, let's say you just needed 1 more electron to fill your shell, okay? And the electronegativity between the 2 atoms is not enough to just pull 1 electron away and give the electron to the other. So we now, instead of doing where we pull electrons away, we now have to share the electrons, okay? So covalent bonding doesn't mean you're sharing electrons equally. It just means that they're shared between the 2 atoms, and they're shared for enough of the time that both atoms feel their orbitals are full, okay? So what this means is that the electron spends part of the time close enough to one of the atoms that it makes that have a full shell, and part of the time the electron is next to the other atom, So it has a full shell. That's what covalent bonding is. We're sharing the electrons over enough of time that we have both atoms have a complete outer shell. Okay. So in the case of this, like if this was hydrogen here, hydrogen starts out as an atom with one electron in its s orbital. It wants two. And so this atom has one electron in its s orbital. So instead of being one negative and one positive, because they have the same electronegativity, it's like, okay, let's just share our electrons part of the time. And that means the electrons spend more of the time in between the two nuclei, right? Because you have the two nuclei that are positively charged forcing each other apart. You have the two electrons forcing each other apart, but then the electrons are pulling the positive charge in. And so you're balancing all of your charges between the electrons and the nucleus to allow you to form this bond. Okay, so what does this mean? So if we're sharing two electrons between two nuclei, we have a covalent bond. So all covalent bonds, all covalent bonds consist of two electrons. Okay, we have different types of bonds, but all covalent bonds consist of two electrons. Okay. Will the sides always be positive and negative? It won't be a specific size. The one that's more electronegative will always be the more negative side. The atom that's more electropositive will always be on the positive side. Okay, so partially positive. So I think, does that answer your question? Okay. So the whole point of this sharing here is the idea that the two nuclei are positively charged and are actually trying to repel each other. The electrons spend more time in the middle, and so those are pulling those in. So there's this delicate balance between the repulsion of the two electrons, the repulsion of the two nuclei, and by sharing all of this energy, by sharing these electrons, it has a net stabilization, and we end up with a nice stable bond that then gives us a way to have complex chemical compounds. Right. All right, next slide. Okay, so we can look at that from an energy diagram perspective, okay? So if you have those two hydrogens again, where you have the electrons together, and you try to squeeze them really close together so the electrons are closer together and the nuclei are close together, it takes energy to do this. So if we look on this side of the graph here, it's actually very hard to squeeze the two nuclei really, really close together, okay? Now, as we go a little bit further away, as we get to this good balance between the positive charges repulsing each other and the negative charges attracting each other, we have this nice intermediate distance where everything's kind of balancing out. When it balances out, that's the lowest amount of energy needed to make that bond, and therefore it's nice and stable, and we can use these things like diatomic hydrogen. However, if we start to pull these away, now the electrons are no longer are attracted to the positive of each of these. They're just trying to repulse each other. The energy goes up again until they're so far apart, they just can't see each other. And so there's no energy loss at all. So if you squeeze them too close together, it takes too much energy because your positive charges can see each other and your negative charges can see each other and not counterbalancing out. But if you can find that great balance point, you end up with a nice stable bond. Now, the cool thing is that balance point also becomes the bond length of that particular bond. So a carbon-carbon bond length is 1.2 angstroms because that's the perfect balance point. For hydrogen, it just happens to be 0.74 angstroms. So that bond length is that perfect balance point in energy versus distance. Oops, nope. There we go. Okay, so now let's take our last 20 minutes here and focus on valence bond theory. Okay, any questions about bonding before I go on to this? The valence bond theory is going to help us to show, number one, how many bonds are going to form, what kind of bonds they're going to form, and we have some generalized rules about different atoms doing kind of funny things. Okay. All right. So what I'm going to do is I'm going to continue on with valence bond theory. Okay. So G.N. Lewis actually did a lot of stuff for us, specifically with the figuring out the nature of bonds. Okay. And what he kind of summarized was the fact that most of the main groups, and those are like carbon, nitrogen, hydrogen, will either gain, lose, or share electrons in order to achieve 8 electrons in its outer shell. Okay. So that came to be the octet rule. Now, this doesn't work for a couple elements, and I'll talk to you about that. But most of the group elements have a total of 4 valence orbitals, and they want to have those completely filled. There's an s orbital, which has 2 electrons on it, and there's 3 p orbitals, each having 2 electrons on it, for a total of 6 p orbitals, for a total of 8 electrons. And those are the 8 electrons we get to deal with when we talk about organic chemical bonding. Okay, so how do we use this, where the electrons are, to help us predict the structure of molecules? This is what we call the Lewis dot structure. And a Lewis dot structure, we build from only looking at the valence electrons and trying to figure out how they all fit together so we can create molecular formulas. Okay. Remember, each of these things, we're going to try to share 2 electrons to make a single bond. And we want to know that we have all of our valences filled correctly. So we're looking to put hydrogen, we want 2 electrons on it. For boron, we want 3 electrons on it. For almost everything else, we are looking for 8 electrons, except for phosphorus and sulfur. I'll talk about that later. Okay, so the first step we do is we determine how many valence electrons we have in the molecule. In a single atom, it's easy. You just look on the periodic table and you can look what group it is, and that's how many valence electrons are on that specific atom. For a molecule, you have to sum up all of the atoms together, okay? And sometimes we have what we call polyatomic ions. It can be an anion or a cation. If it's a polyatomic anion, that means it has an extra electron for each charge. Why? In our atomic carbon, it has 0 charge. It has as many electrons as it has protons, and therefore it has 0 charge. However, if you have a charged element, if you have a charged carbon, that means you've added an electron to it, so it has more electrons than it has neutrons. That's why when we have a polyatomic or multiple atoms together to make an anion, you have to add 1 electron. Now, if you have a cation, that means you have to subtract 1 electron. And that'll become apparent when we do certain things like carbonic acid or carboxylates. Okay, so let's look at a set of these right here. Let's look in particular at this one right here. To start with, we have hydrogen, okay? That is in group 1A. That means that each hydrogen has 1 electron. So we have a total of 2 hydrogens, so we have 2 electrons. Carbon, it's in group 4A. So we have 4 electrons right here. And oxygen is in group 6A, which means we have 6 electrons. So we have a total of 12 electrons to play with, okay? And we can do this for all these others. What I'd like to do is actually demonstrate 3 of them and then have you go back and look at these and see if you can come up with the same answers we get here, okay? So the next one here, we have phosphorus. And phosphorus is going to be kind of funny, so I'll do this one as well. Has 5 electrons because it's in the 5A. Oxygen's in 6A, and fluorine is in 7A. However, we have 3 of them. So we have to multiply 7 times 3, which is 21, plus the 11 here gives us a total of 32 electrons. And then the last one I want to do is this NO, okay? So it's nitric oxide, nitrous oxide? No, anyway, it's got 5 electrons for the nitrogen and 6 electrons for the oxygen, for a total of 11 electrons. That's going to make a very unusual structure, I bet. Okay, so the next thing we do is we find the central atom. Okay, the central atom is usually the atom with the lowest electronegativity, except for hydrogen. Okay, so in the case of these things, think of carbon is typically one of the lower electronegativity atoms, because the electronegativity goes down as you go across the table, and it goes down as you go down the table. So you can think of fluorine being the highest and rubidium being the lowest. Everything kind of goes away from there. So you can just look at a periodic table and kind of predict where it was going to be. So in the case of carbon, we're going to put carbon at the center, and we're going to try to figure out where everything else is. In the case of POF3, we're going to put phosphorus in there because it's in group 5. This is in group 6. This is in group 7. So this is going to have the lowest electronegativity. This is group 5 and group 6. So the nitrogen is going to be in the center here. So we pick the one with lower electronegativity. Okay. And then we try to put all the other atoms around if possible. So in the case of H2CO, we have an H, an H. We're going to put 2 electrons here, 2 electrons here, and the 2 electrons here to show that we have bonds. Okay. Now, I want to stress that you have to count a line as 2 electrons. Okay. So that's the important part here. Each bond consists of a line and counts as 2 electrons. For all row 2 elements, that's the carbon, nitrogen, oxygen, fluorine, you cannot exceed 8 electrons. That's the octet rule. However, in the case of phosphorus, we can, because it's actually a group 3. And so that's one of the weird ones that we can actually add more to. And then, of course, these two, we can only draw the one line between them. Okay, so now we've drawn a line to each of the other atoms in our system, but we're not done yet. Okay, we need to know exactly how many bonds we have, because that tells me how many electrons we've already used. But now we've got to put all the other electrons in. Okay, so in the first case here, we had a total of 12 electrons. And so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 7, 8, 9, 10, 11, 12. So we put 12 of these electrons here. Actually, we had more than 12 electrons, didn't we? We had 12 electrons, 32 electrons, and 11 electrons. Good. So we have 12 electrons, sorry. So we've added the electrons to this system now. Now we have a total of 12 electrons, right? We have, this is 2 electrons, this is 2 electrons, and then we have the rest, the other 6 electrons, and then this is 2 electrons. So we have a total of 12 electrons, okay? But we're not done yet because that doesn't look quite right. All right, let's look at the phosphorus here. So we had 32 electrons, so we have 1, 2, 3, 4, 5, 6, 7, 8. And that means we had to fill in all these other ones right here to give us a total of 32 electrons. There's 6 times 4 plus the 8 in the middle, giving us the. And now when we fill in the number of electrons in this last one, we had to fill in 11 electrons. So we had the 1, 2, and so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Notice that I put more electrons on the oxygen than the nitrogen, okay? The reason there are more electrons on the oxygen than the nitrogen is it is more electronegative, okay? Okay, so now if there are electrons remaining, you need to add them as non-bonding electrons to the central atom. So notice also here, this one has a non-bonding electron in the central atom. Okay, this is because you want to make sure that you have, a bunch of different, you want to have all your electrons accounted for, whether or not they're paired or not. Okay, the total number of electrons on your row 2 elements cannot exceed 8. Your total number of electrons on a row 3 is 8 to 10 to rarely 12. So we're wanted, but again, your carbon, nitrogen, oxygen, those are going to want 8 electrons around them. So how do we use that to our advantage? We go ahead and figure out a way that we can maybe use one of those pairs of electrons to make each atom have an octet. So when we first drew our structure here, we drew it like this, and then we added our electrons to the top here. Okay, So now let's count the number of electrons around that oxygen. And you have to think about that any bond between them, that's a shared electron, so only one of those electrons counts. So we have 1, 2, 3, 4, 5, 6, and then one electron here. So this has 7 electrons around it, but it wants 8. And this one has 1, 2, 3, and 4, 5, 6, but it only has 6 electrons around it. This carbon only has 6 electrons around it. So how do we solve this problem? Well, if we share one of these lone pairs with the carbon to give a second bond, we now have a total of 8 electrons. Notice I'm counting all of these electrons right here. All of these bonds count. Those are 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8 electrons around carbon. And if we look at this oxygen, there's now 8 electrons around oxygen. We had 8 electrons around oxygen here, but we only had 6 electrons around the carbon. And of course, hydrogen only needs 2, so the hydrogens are satisfied. So we have taken our system, number of valence electrons, added our central element, shown where our bonds are, added all of the other electrons, and now we're looking for having our things have octets if at all possible. So let's try to do that with nitrogen here. We can do the same thing. The oxygen can share its pair of electrons to form a double bond. And now we have 1, 2, 3, 4, 5, 6, 7, 8 electrons around oxygen. But we have 1, 2, 3, 4, 5, 6, 7 electrons around nitrogen. Okay. But remember, we only had 11 electrons to deal with. So we have all the electrons we have, but it has to be this way. And notice that the least electronegative atom has the unpaired electron. Now, if we do this for this NO2 right here, what we can do is we can actually end up with our nitrogen having 8 electrons around it and all of the oxygens having 8 electrons around it. So we can do that. All right, so that's the last thing we need to do to make sure we have it. Now we have to figure out what if there is a charge on any of the elements, okay? And so again, when we drew our thing here, we don't have 8 electrons around nitrogen, okay? So that's going to tell us something about the nature of that part of the molecule. So we need to figure out, have we balanced all the charges around? And so that's what we call calculating formal charge, okay? So to calculate formal charge, we need to have an equation. Formal charge, or the charge on that specific element. We have to calculate formal charge for each element separately. Formal charge is equal to the number of valence electrons of the neutral element, okay? So let's do the one that's, let's do the carbon with the oxygen and this one first right here. We're going to do the carbon on this one. We're going to do the oxygen on this one. Then we're going to do the NO2, the NO one. So carbon had 4 valence electrons in its neutral element because it was on group 4A, okay? But then we need to subtract any non-bonding electrons. And we don't see there's non-bonding electrons up here. This lone pair is up here on oxygen. Those are non-bonding. We don't have any of those on carbon, so that's going to be a 0. But plus 1/2 of the bonding electrons. What? 1/2 of the bonding electrons? Why? Well, we're sharing the electrons between 2 atoms, right? So we can only count 100% of one of the electrons toward the charge of the center atom. So this side, we can only count one of these electrons would counterbalance the hydrogen here, but we can only count for one counterbalancing the charge on the carbon. So that's why we have 1/2 of the bonding electrons. So here we have 1, 2, 3, 4 bonds. Each of those bonds has 2 electrons. So we have 8 bonding electrons right here. And if we do our simple calculus here, our formal charge is equal to 4 minus 0 plus, I got it. No, it should be minus. This should be a minus, sorry. Minus 4, making our formal charge on carbon 0. I have the equation written wrong here. Let me correct that on my next slide. Okay, so our valence electrons we had minus this gives us a total charge on carbon of 0. Now, if we do the same thing for oxygen here, we're going to have a total of 6 electrons because it's in group 6A, minus 4. I think it's going to be plus 4. I think these two elements are switched here. Minus 1/2 of the bonding electrons, which is 1/2 of 4. 1/2 of 4, which is 2, which means its formal charge is also 6 minus 4 plus, no, that's right. I don't know. It should be equal to 0 as well. Formal charge.
I think, so the number of non-bonding and the plus half are like in parentheses, so they would like get the negative.
Do them first. Yeah,
Yeah.
you're right. I'm sorry. I forgot my brackets.
That's okay.
I told you it was simple calculus. So we have our brackets here. So 4 plus 0 is 4, minus 4 is equal to 0. And we do that again here. We have 4 plus 1/2 of 4, which is, this is again a minus. Thank you for seeing that. I missed the bracket, which gives us a formal charge of 0. Okay, now let's do that same calculation on NO. NO. So there's 1 here, and there's that odd electron here. Okay, we're going to do it with the nitrogen here. So the formal charge is equal to the number of valence electrons. Nitrogen is in group 5A, so that gives us a 5, minus bracket. Let's see, the non-bonding electrons, we have 1, 2, 3, 3, plus 1/2 of the bonding electrons. We have 1, 2, 3, 4, because we have 2 bonds here, and that's a total of 4 electrons. 1/2 of 4 right there, which makes it 5 minus, let's see, 1/2 of 4 is 3, and which is 3 plus 2. So that gives us 5, which means the formal charge on nitrogen is 0. Even though it has an odd number of electrons, the formal charge on nitrogen is still 0. And we can do that on the oxygen here too, which means the molecule itself has no charge. That's where it comes into formal charges. So if we add up all the formal charges on all of the atoms in a compound, that gives us the charge of the entire species. Okay, so in summary, we can use these Lewis dot structures to tell us how many times some things are going to bond, where those bonds are going to be, and how many non-bonding electrons we have. And then we can go back and calculate our system. So again, we start with trying to keep our low electronegative atoms toward the middle. Right here, we're going to add the electrons we have around each of them. We're going to turn each of these into a bond to try to get it arranged in a way that looks reasonable. And then we're going to move electrons around until we have an octet on all the group 2 elements, 2 electrons on hydrogen, and up to 12 electrons on group 3 elements. Yeah, so most of the time our formal charge will be 0, but we can actually do some more with that. So let me, I'm going to stop here actually and do that charge systems next time. We are right at 9:20. I'm sorry, I went over a little bit, but we will continue this on Thursday. Look for little short videos with each of these being separately called out, and hopefully corrections in my calculations next time. Okay. So yes, formal charge is 0. The more electronegative means more likely to attract electrons. Yes. And let's see, one more question up there. Would CO have a double bond? I think that is true. Does more atoms equate to more electronegative? No, electronegativity is specific to each element. And so it just tells you whether the charge is going to be polar or not. Okay. So if I didn't get to your question, go ahead and email me or come in next time. I'll see you on Thursday. Thank you very much.
Thank you.
Thank you.
Thank you, sir.
Yeah.
Very good.
Let me
Thank you.
stop sharing. Oh, that's not where. There we go.